Okay, I'd like to open this section by recalling the hierarchy of functions mentioned in an earlier section, and just reminding you of how we can use this hierarchy to take advantage of direct comparison. So I'm going to use the double less than notation here in this context to mean that the function on the left grows much slower than the function on the right, or you can think of it as the inequality is eventually true if it's not true right away. So let's get our hierarchy of functions. So 0 is eventually less than 1, of course it always is, which is eventually less than the natural log of n, which is eventually less than n raised to a power, well, non-negative, which is eventually less than an exponential, and it doesn't really matter what the base is, which is eventually less than factorial, and factorial itself is dwarfed by n to the n. Just as a quick example of using this, we could say that natural log of n is less than or equal to, say, the square root of n, which is in the category n to the p. This is eventually true. Looking at their graphs, it might not even be obvious because they both have sort of a shape like this, right? But you can count on this being eventually true, meaning for large enough n, this is true, and when it takes hold, it'll be that way forever for all larger values of n. So, for instance, if you're working with this series, well, you can use direct comparison test, because we can say that natural log of n over n squared is less than or equal to rad n over n squared. And this is equal to 1 over n to the 3/2. And of course, this p series here converges because 1.5 is strictly greater than 1. And therefore, this series converges. All right. Notice that it was a good decision to do the rad n, while it is true that ln of n is less than or equal to simply n. Had we done this particular comparison, then we are showing that ln of n over n squared is smaller than 1 over n, which is the term of a harmonic series. And the terms of a series being smaller than the terms of a divergent series is meaningless, right? That's not the direction of comparison we need to establish anything. So of course, with direct comparison test, you need to show that the terms of the series you're interested in are either smaller than the terms of a known convergent series or greater than the terms of a known divergent series. All right, by this stage in the game, you should hopefully be looking at this particular series and going, hey, that's purely algebraic. Let's go to the limit comparison test. And yeah, that is a winning strategy. So by all means, we should do that. So what is the p-series this is going to behave like? Well, we clear away the clutter and take the leading term from the numerator and the leading term from the denominator, which is n over n cubed here, and that is 1 over n squared. So we know that this series is going to behave like 1 over n squared, which is a convergent p-series. So all we have to do is actually prove it. Okay, well, let's let c be the limit as n approaches infinity of an over bn. So an is our original series, and dividing by bn is like multiplying by the reciprocal of bn. And you can see that this is a purely algebraic limit with degree 3 in the numerator, degree 3 in the denominator. So it's just going to be the quotient of leading coefficients, which is 1 over 1 in this case. All right. And 1 is strictly greater than 0 and strictly less than infinity. So we can conclude that the two series have the same behavior. Okay, well, what is the behavior? Well, the easy one, the one we compared to, this guy's convergent. Why? It's a p-series. 2 is strictly greater than 1. So our conclusion is that the series that we're interested in is also convergent. And there we are. Now, yes, it is true that limit comparison test will always work on a purely algebraic series, provided you know how to select the right series to compare it with. However, this particular one could also be dispatched using the direct comparison test, which would have been a little bit shorter. And that's just because, luckily, it's constructed in that perfect way. So notice that this guy here is less than or equal to n. The numerator is certainly true that that's less than, and the denominator is greater than n cubed. So overall, we can say this is less than or equal to n over n cubed, which is 1 over n squared. So great. That's the first step of direct comparison, is establishing the comparison, and it's the direction that we need. Then we can say this guy is convergent, and we can conclude that this is convergent. So yeah, luckily direct comparison test worked here. If this original problem had some other arrangement of pluses and minuses, then perhaps direct comparison may not have worked quite as easily. There's often ways you can make it work, but as always, it's safe just to go to limit comparison test when you have a purely algebraic series. All right, so really at this point, everyone should be looking at this and going, purely algebraic, limit comparison test, and the only real challenge is determining what the thing is we have to compare it to. It's going to be some kind of a p-series. So let's take the leading term from the numerator, which is the cube root of n squared. And we'll divide that by the leading term of the denominator, which is 3n squared. And you don't even need the 3. Let's clean this up until we have a clear and obvious p-series. So this is n to the 2/3 divided by n squared. So this is 1 over n to the 2 minus 2/3, which is 1 over n to the 4/3. And that is the series to which we will compare our original series. Notice at this point in the game, we know how everything's going to play out. We know the limit comparison test will tie their behaviors together. We know this is a convergent p-series because 4/3 is greater than 1. And therefore, we know this is a convergent series. It's all about writing the proof. Let's let C be the limit as n approaches infinity of that ratio. There's our an multiplied by the reciprocal of bn. And this limit is purely algebraic. The numerator's degree is 2, right? It's 2/3 plus 4/3, which is 6/3, and that's 2. And the denominator more clearly has a degree of 2. So these are matching degrees, of course, because we carefully selected the series Bn. So this is going to come out to the ratio of leading coefficients, which in this case is 1/3. If we had kept the 3 up here and had that 3 tracking all the way down, we would have had a 3 here, and the ratio at that point would be 3 over 3, which comes out to 1. So it doesn't matter, the conclusion would still be the same, which is that C is a finite number positive, so greater than 0, less than infinity. And of course this is convergent because 4/3 is greater than 1. So our conclusion is that that other thing, I don't want to write it, so we'll just go sigma an is convergent. Okay, very good. Okay, let's check out this series here. What is a hyperbolic function doing here? Hyperbolic functions are such an annoyance. So while it's fair that you might not know the definition of such right off the top of your head, you ought to be able to reconstruct it because you should know the definition of cosh. So let's just recall that cosh of n, or cosh of whatever, is e to the thing plus e to the negative of the thing divided by 2. So hopefully you know that. And therefore, you can deduce that sech would be the reciprocal of that, as the reciprocal relationships from trigonometry apply here in hyperbolic functions. So sech would be 2 over that thing, which means we can go right to our problem, and we can write it as 2 over e to the n plus e to the negative n. And now figure out what to do with this thing. So I've said in the past that one of the most powerful applications of the direct comparison test is for throwing away unwanted terms. So let's use the direct comparison test. So let's see how we can use the direct comparison test to great advantage in this particular situation. Well, let's just throw away this e to the negative n, because we can certainly see that this entire expression is less than or equal to 2 over e to the n, since this denominator here is obviously greater than this denominator, and they have the same numerator. So really, we're asking ourselves, what's the behavior of that series? Well, that's a geometric series, and hopefully you can see that the r value is 1 over e. So absolute value of 1 over e is 1 over e, which is less than 1. So we have a convergent geometric series here. Well, that's enough from the direct comparison test to draw the conclusion that our original series is convergent. So all that's left is to properly articulate this. Well, we've got step 1, which is establishing the comparison. So now we need to show that this guy is convergent, and geometric series are very easy to prove. They're one-liners like p-series, right? The absolute value of r here is 1 over e, and 1 over e is less than 1. How do we know that the r value is 1 over e? Well, this series can be written like that, and that makes it a little more clear that our r value is 1 over e. It's basically the stuff in a geometric series that is raised to a power. Okay, so let's draw our conclusion. And let's draw it about the original series even, sech. Sech of n is convergent. Cool, that was a cinch. So let's take a look at this one here. You may be seeing that factorial and thinking, sweet, let's use the ratio test. And it's true, if you have a factorial, you should try to find a way to use the ratio test. And we will definitely be using the ratio test. But the ratio test is very troublesome when you have a plus or a minus in the problem, as we do here. So before we do the ratio test, we should try to figure out a way of getting rid of that 1. The problem is that this is actually going to turn out to be a convergent series. And we can make that speculation because of the fact that the factorial is going to dominate the exponential growth in the numerator. So that alone is never proof. That's just enough to give you some speculation, though. So we can guess that this is going to be convergent. And since this is convergent, we can't just throw away that 1 because it's being added in. In other words, we can't just say, well, this guy here is smaller than, say, this guy here, because that's just not true. So that's how we typically use direct comparison to throw away a term. We would be able to do that, of course, if this were a minus 1, no problem. Then we'd get the direction of comparison that we need, run the ratio test on that particular term, and we would get everything we need to conclude the original series is convergent. So yeah, this is problematic. But no problem, because that plus is in the numerator, which means we can split this into two separate series. So instead, let's write it as follows. And now we will just test the convergence or divergence of A and B. So A is this guy, of course, 2 to the n over 2n factorial. Single term over single term, there's a factorial there. So hot dog, we can do the ratio test. All right, well, everything's positive, so we don't need the absolute values. And let's spend a moment to line everything up with its friend. So we'll put the exponentials together. We have a pending factorial battle here. Distributing the 2 goes 2n plus 2 down there. So 2 to the n plus 1 over 2 to the n is just 2. And over here, to resolve the factorial battle, we need to begin to unwrap whatever the larger one is. That would be the bottom one. 2n plus 2. 1 less than that is 2n plus 1. 1 less than that is 2n factorial. Great. There's our cancellation. So what do we have? We have 2 over 2n plus 2, 2n plus 1. This limit is going to evaluate to 0. And what is it about 0 from which we can draw a conclusion? 0 is less than 1. Therefore, the series we're dealing with, which I'm going to actually write explicitly just because there's a number of series in this question at this point, is convergent. Okay, so that first series is convergent. Now we just need to show that the other series is convergent, and we get to conclude that the sum of those series must also be convergent. Now, you might look at this guy and think, let's use the ratio test. We know it's going to work. And that's true. You totally could. However, why don't we use direct comparison test with this series and compare the series we're interested in with the series we literally just established is convergent, because the terms of this series are smaller than the terms of that series. So that seems like a pretty efficient way to go. So specifically, that is clearly smaller. It's much smaller, in fact, than this thing. And we know that this is a convergent series. We just established that using the ratio test. So we can conclude that this series is convergent. So now that means that the original series, which was the sum of those two convergent series, must also be convergent. Okay, so there we are. At this point, we have made it through the parade of series tests. And I think it's a good idea if we just go back to a few select topics and talk about them now that you've kind of gone through your homework. And one of those topics that I like to revisit is classifying an alternating series as absolutely convergent, conditionally convergent, or divergent. So let's quickly look at an example. All right, so here, of course, we have an alternating series. So it's going to fall into one of these three categories. This factorial here strongly suggests that we ought to consider the ratio test for this. Now, if we do the ratio test and we actually get convergence out of the ratio test, we immediately get to conclude absolute convergence. So if you can find a way to use the ratio test, again, that's great, provided that the thing actually is absolutely convergent. and provided it's not purely algebraic, as you know, the ratio test would be a waste of time for that. So let's use the ratio test. Here, the absolute value will actually have some value because we're putting in an alternating series. So we know that the absolute value is going to essentially counteract the -1 power. Let's put it in for the moment, though. So we have -1 to the n plus 1, and then we have n plus 1 plus 1 over n plus 1 factorial, 3 to the n plus 1. So that was all an plus 1, and then we're going to divide by an. So that's like multiplying by the reciprocal of an. So we have -1 to the n here, and then we have an n factorial up there. So again, we can throw away these -1s. First, they actually combine to just simply be a single -1, but that gets thrown away because of the absolute values. And now let's line everything up with its friend. We have 3 categories of factors here. We have some sort of algebraic stuff, like this n plus 2, which we can put with the n plus 1. We have 3 to the n plus 1, which we can put with 3 to the n. And we have n factorial, which we'll put with n plus 1 factorial. Of course, we'll have a factorial battle. Those are my favorite. The 3 to the stuff, that just resolves to simply 3. And here we have 1 over n plus 1. Okay, so what does this limit equal? Well, this is a purely algebraic limit at this point. The numerator has degree 1, and the denominator has degree 2. So with the denominator having a higher degree than the numerator, this limit automatically approaches 0. Okay, what is it about 0? Well, it's less than 1. And therefore, we get to draw our conclusion immediately about the original alternating series. All right, very good. All right, same imperative as before. Classify as absolutely, conditionally convergent, or divergent. The difference here is that the absolute version of this series is purely algebraic, which means that the ratio test will be inconclusive. So if we waste our time with the ratio test, we're going to get an L value of 1, which means nothing. It means we've wasted our time. All right, well, so we still don't know anything about this series. Well, let's take a look at it. We can run an alternating series test in our head. That's one of the nice things about it. If we took the limit of this particular term as n approaches infinity, you could see that that limit would approach 0. So that tells us that at least this is a convergent series, which means that we rule out the case of it being divergent, of course. So all we have to do is classify the series as absolutely convergent or conditionally convergent. And that involves investigating simply the behavior of the series without the -1. So this is the absolute version of that series. Now, what is the behavior here? Well, who cares what context we're in anymore? We are deciding whether this series right here is convergent or divergent. So, okay, it's purely algebraic, right? So we'll compare it with a p-series using the limit comparison test. What p-series should we compare it to? Well, leading term divided by leading term, say 4 over n, or 1 over n, right? Either way, that's the harmonic series. So we know that this series here is going to be divergent because we know we can tie its behavior to the harmonic series. That means we can conclude the original series is conditionally convergent. All right, wonderful. We just have to prove everything now. So to show that a series is conditionally convergent, you need to do 2 things. You need to show the absolute version is divergent, and you need to show the original version with the alternating sign is convergent. So we'll use the limit comparison test here with, just go with the regular harmonic series. So this limit here approaches 4. Okay, what is it about 4 from which we can draw a conclusion? Well, 4 is greater than 0 and less than infinity. So therefore, these two series have the same behavior. Okay, we need to acknowledge the series we're comparing to is divergent. Why is that? You could just use the word harmonic. That's enough. We all know that the harmonic series is divergent. Or you could say it's a p-series. P is equal to 1, and 1 is less than or equal to 1. Right, harmonic's enough. We can conclude here that this series here is divergent. Okay, so now we just need to show that the original series is convergent using the alternating series test. All right, so the alternating series test has us checking a few things. Is this true? Yes. Both the numerator and the denominator are increasing, but the denominator is increasing at a faster rate. So we can acknowledge this. And the other thing to acknowledge is this limit here. Is it equal to 0? Of course. So therefore, by the alternating series test, this series here is convergent. All right. So our conclusion here is that since this guy here is convergent and the absolute version of that series is divergent, we get to conclude that this series here is conditionally convergent. Okay. Okay, let's revisit this particular type of problem. So this is a geometric series, and we want to extract the r value out of this, so we can write it as e to the negative x, which itself is raised to the n. And you can see here is our r value. R is just the stuff that's raised to the n. But also, if you're not quite comfortable with that, and we're going to need our a value anyway, since it's asking for the sum, you can certainly write out the terms of the series, because you know that the first term of the series will be a, and the second term of the series will be ar. You know that when it's a geometric series. So the first term of this is going to be e to the negative x to the 0, which is of course just 1, plus the next term of this series, which will be e to the negative x to the first power, plus, who cares, right? At this point, we have our a, which is 1, and we see that ar is e to the negative x, but a is 1, so we have r equals e to the negative x. Okay, so in order to answer the question, determine the x values, we're going to set the conditions up for convergence here. So we know that the series converges when the absolute value of r is strictly less than 1. So that would be the absolute value of e to the negative x being strictly less than 1. Okay, well, e to the stuff is naturally positive, so we don't need the absolute values there. And let's just solve for x in this inequality. Okay, well, you can safely take the natural log of both sides of an inequality, because natural log is a monotonically increasing function. So we're going to get negative x is less than the natural log of 1. And of course, this means that x is strictly positive. So we could say that the interval of convergence is 0 to infinity. Interval of convergence is a term that's going to come in section 11.8. Basically means the interval of x values for which a series is convergent, which is exactly what this question is asking. The next question is find the sum of the series. Okay, well, the sum of the series is a over 1 minus r. Well, we found a earlier to be 1, and we found r to be, of course, e to the negative x. So that's a perfectly good answer. But we could also write this as e to the x over e to the x minus 1 if you wish. All right, I always like to end this particular lecture with a sequence example because it's been so long since we've seen sequences. A very common mistake I see is students applying series tests to check for the convergence of a sequence. But series tests simply do not apply to sequences. So the ratio test, root test, whatever, they don't apply. To determine whether a sequence converges or diverges, you take the limit. All right, if the limit exists and is finite, then you have convergence. And the limit of the sequence is whatever the limit of the limit is. So great, let's do that. All right, so where's this limit running off to? Well, the base is natural log of n, and as n approaches infinity, the base here, natural log of n, approaches infinity. The exponent is 1 over n, so as n approaches infinity, the exponent approaches 0. So we have a bit of a dual here. We have infinity raised to the 0, which is an indeterminate form. So the way we handle that is using L'Hopital's rule. Of course, we have to do several things. One is, of course, we can't apply L'Hopital's rule to the terms of a sequence because they're not differentiable. So we have to construct an interpolating function, right? This differentiable f of x. But even when we do that, we still have the problem of this not being in the form of infinity over infinity or 0 over 0, right? So of course we have to do some manipulation, and when you have an exponential indeterminate form, that manipulation is usually introducing a natural log to bring everything down to the same level. Okay, let's do all of that. So first we'll let f of x be ln of x to the 1 over x. And now we are going to evaluate this limit. So, of course, no surprise, we're getting the same form, infinity over 0. All right, so here we will let y equal the expression, and writing y equals the expression allows us to take the ln of both sides. So we get ln of y is 1 over x times ln of x. And what are we after? Well, we are after the limit as x approaches infinity of y. So let's not forget that. Back down here, let's take the limit as x approaches infinity of both sides. Okay, well, strictly speaking, the way we have this written, 1 over x approaches 0, and ln of x approaches infinity. Of course, extremely slowly, but it does approach infinity. So we have 0 times infinity here. Still an indeterminate form, much more manageable than the exponential indeterminate forms. But of course, in order to use L'Hopital's rule, we need 0 over 0 or infinity over infinity. So we'll write this, of course, as ln of x over x. That wasn't too hard. Sometimes it's a little more complicated than that, but this one's nice. So what do we get? Finally, a form where we can directly apply L'Hopital's rule. Okay, so the derivative of ln of x with the chain rule is 1 over x ln x. And the derivative of x is 1. So now, if we let x approach infinity, we can quite clearly see that this limit evaluates to 0. Okay, well, all along, what was the left-hand side? That was the limit as x approaches infinity of ln of y. So let's push the limit inside the natural log function, like so. Because natural log is continuous, we can now exponentiate both sides, which of course that gives us 1 on the right-hand side. And, well, What was our y? Our y was ln of x to the 1 over x. So that's equal to 1. But even better, this applies to our sequence, of course. And so we can now draw the conclusion that this sequence converges and the limit is 1. So sequence converges to 1.